Hello, my dear students. Welcome to the session. Let's look at other problems here. I think you have finished this, right? So let's look at 37 problem. Okay. .37 problem. Okay. Question number 37. The current passing a point in a device is shown in the following figure. Read that, all of you. The current passing a point in a device is shown in the following figure. Calculate the total charge to the point. That's the question, right? Classroom workbook, question number 37. I is in milliampere, time is in millisecond. Okay. Classroom workbook 37. The current passing a point in a device is shown in the figure, following figure. And we will see even the alternative solution for that also. Okay. Look at this first. Now, let us define first of all mathematically what is current here. 0 to 1, it is 10 by 1, that is 10t for t between 0 to 1. Similarly, after that you have 10 between 1 to 2. Okay. Now, what is actually charge? Total charge. He is asking total charge. That means what? Total charge means charge between 0 to 2 or else charge at an instant 2. Both are same. I told you already that charge between t0 to t is same as charge at an instant t. Both are same. When integration is there, this interpretation is okay for us. So q of t, that is nothing but q of 2. Okay, q of 2 is equal to q of 0. The lower limit, if I take 0, then integration 0 to 2 I am supposed to take here, I of t dt. But do you have any information regarding q of 0, q of 0? Directly or indirectly the information is not given, then we can consider to be 0. But always have a practice of writing that particular quantity. Now 0 to 2 can be split into 0 to 1 plus 1 to 2. Okay, this is 10 dt, 10t dt, and this is 10 dt, yes or no? Okay, so 10t dt is nothing but 10t square by 2 plus this is 10t. Okay, this is 1 to 2. This is actually 0 to 1. Now tell me, what do you get here? What do you get here? Okay, we can take it out. This is 5. Okay, 5 into 1 square minus 0 square plus 10 into 2 minus 1. So this is 5, this is 10, then 15. But 15 what? Milliampere into millisecond. What is actually charge? Charge is nothing but current into time. Milliampere into millisecond will give you microcoulomb. Understand all of you, okay? Milliampere into millisecond will give you microcoulomb. You got this answer. But you also know that q of 2 is nothing but q of 0 plus area under I of t over the limits 0 to 2, yes or no? 0 to 2, 0 to 2. You can write, this is 0. The area you can find. What is this actually? It's a triangle plus rectangle, or else you can take completely trapezoid. 0 to 2, what is the area? Area of a trapezoid. Trapezoid area formula, I think all of you know very well. H by 2 a plus b. H means height, a means longer one, longer side, and b means shorter one, right? Therefore h by 2 area is nothing but h by 2, that is nothing but 10 by 2, okay, into 2 plus what is this? 1, right? So 1. So what do you get here? This is nothing but 10, 3 ja, 30 by 2. This is 15. But area is nothing but what? Y-axis quantity into x-axis quantity. Slope is nothing but y-axis quantity divided by x-axis quantity. But area is y-axis quantity into x-axis quantity. So milliampere into millisecond will give you microcoulomb. So always try to prefer the area calculation instead of going for the integration. Unnecessary time waste process here. Okay. So please note it down. Note down quickly. Finish that all of you quickly. We will go for a 38 problem. Meanwhile, I just note down 38 problem here, okay? What is the 38 problem actually given here? The current through an element is shown in the following figure, right? I think all of you finished that. Then we'll go for this. I'm just drawing that figure. Current versus time is given here, okay? The current through an element is shown in the following figure. Read that question, all of you. Determine the total charge that passed through the element at t equal to 1 second, b t equal to 3 second, c t equal to 5 second. Okay, so he's asking what is the charge at different instances: 1 second, 3 second, 5 seconds. Okay, so we'll try to find it out. This is what the waveform given. Okay, so this is 1, 2, 3, 4, and 5. So all of you have this problem in 38 problem classroom workbook. Please refer to that figure. And 5, this is 10. Okay. Okay. So I think all of you understand that question. What is asking? Charge at instant 1, Q of 1. What do you mean by Q of 1? It is Q of 0 plus, yes or no? Q of 1 is nothing but what? Q of 0 plus, okay, integration of the current between 0 to 1. But I told you already, okay, when you have the straight lines and all, the shapes are very clear. Okay, you can directly go with the area calculation instead of, okay, integrations and all. So can I write something like this? Q of 1 is nothing but Q of 0 plus the area under I of t between 0 to 1. area of I of t. Okay. What is that q of 0? It didn't mention anywhere, right, in the problem. Directly or indirectly, nowhere it is given. Therefore, you can consider to be 0. Now, area under I of t from 0 to 1. What is 0 to 1 actually here? Can I say something like this? This is area 1, nothing but 10 into 1, 10 coulomb. Okay, next one. Q of 3. Q of 3 means what? From 0 to 3. From 0 to 3. Q of 3 is nothing but 0 to 3. That means you can take, this is area 2, this is area 3. Okay. You can write something like this. Q of 0 plus area under I of t, okay, between 0 to 3. This is already 0. Or else you can write something like this. Q of 1, okay, what will happen when you write this? Tell me, area under I of t from 0 to 3. It is area 1 plus area 2 plus area 3. Okay, or you can write that, Q of 1 plus area from 1 to 3. What's wrong in this? Yes or no? You can write this or this, doesn't make any difference. You can also write the lower limit Q of 1, then 1 to 3 you are supposed to take. But finally it is Q of 3 only. What is Q of 1 actually here? You know that very well. Q of 1 already you determined, right? Q of 1 is again Q of 0 plus area from 0 to 1. That is nothing but A1 plus area from 1 to 3. What is area from 1 to 3? Is area 2 plus area 3. So finally you get the same answer. Area 1 plus area 2 plus area 3. Here also you got the same value, right? Just to make you understand, I'm just elaborating because different problems come in different dimensions. One should have the clarity in how we are calculating in different ways. Okay. So let's go with A1 is 10 plus A2. What is A2? Tell me. H by 2. A plus B can I take? Because the trapezoid, right? Height is how much? 1. A 10, B 5. The trapezoid. H, A, B, right? So H is how much? 1, because this difference is 1, and 10 plus 5 plus area 2 how much? Area 3, sorry. Area 3 how much here? This is 5 and this is 1. 5 into 1. Okay, so what do you get? 10 plus 5, 15, and 15 by 2, 7.5 plus 15, 22.5 coulomb. Okay, now another one. Q of 5 it is. Q of 0 plus area under 0 to 5. That's nothing but what? Area 1 plus area 2 plus area 3 plus it is total. If you can take area 4, then what do you get here? Area 1 plus area 2 plus area 3 plus area 4. That's it. Okay. Or else some people may write like this. Q of 3 plus area between, why can't we write like this? 3 to 5. But what is Q of 3? Already you know very well. A1 plus A2 plus A3. Okay. A1 plus A2 plus A3 plus A4. This value is already determined actually in this problem, 22.5. But area 4, what is area 4? Again trapezoid. Trapezoid height is how much? Okay, this is a trapezoid, right? Okay. Height is how much? 5. So 5 by 2 into, okay, 2 plus 1. So 5 into 3, 7, 15, 15 by 2, 7.5, 7.5 plus 22.5. This is going to be what? 30 coulomb. This is going to be 30 coulomb. Okay, so please note down all this. It's a very, very important problem. Interesting problem that, okay, on the basics. Note down this, all of you. Read the question, problem number 39. Read the question. A fully charged mobile phone is good for 10 minutes talk time. Yes or no? Okay, I think all of you reading that. A fully charged mobile phone is good for 10 minutes talk time. During the talk time, the battery delivers a constant current of 2 ampere. The voltage characteristics of the battery during the talk time is as shown in the following figure. Find the energy of the battery during the talk time. Okay, so let's take, it was actually asked in GATE. Okay, so what is the data given? The battery delivers a constant current of what? 2 amperes. And the voltage characteristics of the battery are shown like this. This is 12. Okay, voltage is given in volts, time is given in second, and this is given as 60 minutes. So 10 minutes, okay? 10 minutes talk time, right? 10 minutes, and this is 10, this point. Okay, the voltage characteristics are shown in the figure, right? So what is it expecting actually? Find the energy of the battery during the talk time. Energy during the talk time. What is the talk time actually? 10 minutes. Okay. Energy during the talk time means energy between 0 to 10 minutes. Or else energy at an instant 10 minutes. Both are same actually. It doesn't make any difference. Because again, energy is nothing but integration of power. Wherever integration is there, you can think like this. I told you already. Okay. So let's write the formula here first. First we do a normal procedure and then we'll see is there any alternative approach. First we see the normal, okay, usual formula how we apply. Look at this all of you. What do you want actually? W of 10 minutes. Actually 10 minutes can be written as what? 600 seconds, right? Okay. So W of 600 is asking. Energy during the talk time is nothing but 0 to 600 seconds. Is nothing but W of 0 plus integration 0 to 600 P of t dt. This is 0 because he did not give any information. Sometimes he will give information, you must be careful. But in this context, no information is given directly or indirectly about W of 0, initial energy. P of t can be written as what? V of t into what? I of t. No doubt. But remember, during this talk time, the battery delivers a constant current. Okay, the battery delivers a constant current. I think it's the best example to understand the current source concept. What does the current source actually does? It supplies the power at a constant current. The voltage across the current source may vary with respect to load. Who is the load here actually? Torque. The more you torque, the more load will be applying here. Now, the more you torque, what is happening? The voltage is varying here. Understand? Okay. The voltage is actually decreasing as the torque time is increasing here. But the battery current is constant. At a constant current, if the device is supplying the power, then that device can be called as a current source. This is how you can visualize the current source actually here. See, current source is not a direct element, it's an indirect element actually. Voltage source is a direct element actually. So current source is derived from the voltage source only. But you can visualize wherever the current is maintained constant here and the voltage is varying with respect to the load, that can be treated as what? A current source. Okay. So best example to understand the current source here, right? Now tell me, what is actually V of t? 0 to 600. Current is actually how much here? 2 ampere. 2 ampere. What is the voltage actually here? Voltage, instead of giving directly that function, he gave a waveform. You can find that voltage. What is the voltage actually? Is a straight line with a negative slope, right? Can we find that straight line with a negative slope? The equation, the 12 comma 0. What is this actually? This point is 0 comma 12, not 12 comma 0, 0 comma 12. This point is what? 600 comma 10. Now what is that equation you are getting? V minus, okay, y minus y1 minus 12 is equal to m, that is 10 minus 12 by 600 minus 0 into t minus 0, right? T minus 0, x minus x1. So therefore from this you understand V is equal to, okay, this is actually minus 2 by 600, that means minus 1 by 300 minus t by 300, okay, plus 12. This is what you are going to get. Okay. Now, if you substitute here, the V of t is actually minus t by 300 plus 12, and current is 2, and this is dt. That's it. You can integrate the whole part and you can simplify, you get the answer. Okay. But the same problem can be solved using a simple approach that, okay, look at this, all of you. Don't write anything, I'll give you time. Look at this. Look at this. Or you can look at this. W of 600 can be written as W of 0 plus area under P of t, right? P of t over 0 to 600. Understand? This is 0, right? This is 0. Now, area under P of t can be written as what? Area under P of t can be written as what? Area under product of V of t and I of t. You cannot write area under V of t into area under I of t. It doesn't work because integration of a into b dt is not equal to integration a dt into integration b dt. Yes or no? It's not possible. But area under the product of V of t into I of t can be written. But in this, what is I of t? I of t is a constant. This is 2 amperes constant given. When you have integration of a into b, in a and b, suppose if a is constant, then can you write a into integration b dt? You can write. That means what? You can take that area under V of t, okay, can be written here into 2. This can be written because the current is constant. Because the current is constant, I can write here. You can mention here, since I of t is constant. Since I of t is constant, you can write 0 to 600. You can look at this now. 2 into area under V of t. Again, it is a trapezoid, Nana. Okay, it's a trapezoid. Trapezoid, what is the height? 600. What is A? 12. What is B? 10. That's it. So therefore, 2 into h by 2, that is 600 by 2. Okay, A. What is A? 12 plus 10. That's it. So 2 get cancelled here, and you get how much it is? 12 plus 10, 22. 22 into 6. 22 into 6. Okay. That is 132. Okay. 0, 0. That's it. So can I say it is 13.2 kilojoule? You get the same answer when you integrate here also. Please, all of you verify it. Okay, I think you are good at integration. Otherwise, I can't help you out. Okay, so 13.2 kilojoule. That's it. I think you understand the point. Without even integration, you can directly solve the problem just by area calculation. Suppose if current is also varying with respect to time, is it possible to apply this? No. In such cases, what you are supposed to do? You have to take current waveform, you have to take voltage waveform, you have to find the product, you have to go for the integration. That is why the first method is also not ruled out. Because tomorrow in the exam, okay, you may not get the same question. Okay, there was one question actually in the inductors and capacitors I'm going to discuss, where you find the energy, okay, with both current as well as voltage is varying. I'm going to explain that problem also. That's why we cannot predict anything. We know shortcut technique, but we should not forget the main technique here. The fundamental things we should not forget here. Understand all of you? Okay. So in GATE, anything may happen. We can't say anything that this type of question will come. Only this will come. We cannot say anything. That is why I always suggest that first you know the standard procedure, then you know the shortcut. And you remember when you are applying actually the shortcut technique, under what condition you are applying the shortcut technique. If you are fully conscious about it, you never commit to any mistake. Understand? Okay. Please note down. Note down this quickly. Okay, I think you have noted down this part, right? You please proceed with that. Meanwhile, I just note another problem here, okay? I think you have also written this, the equation for the voltage. Question number 40, classroom workbook. You can read that question. Before that, I just want to draw it. I think all of you finished that, okay? So let me draw that. What is the question? Actually, the current I of t as shown in the figure is passed through a capacitor. The charge in microcoulomb acquired by the capacitor after 5 microseconds is, okay? The charge in microcoulomb, okay? So I think you understand this, right? So this is actually, this is 5 and this is actually given 3. This is given actually here 3, 4, 5, 6, 7. Right? Okay. So this is how actually the problem given, I mean the waveform given. This is current I of t amperes. This is in microsecond. Okay. Current versus microsecond. Current is in amperes and time is in microsecond. Okay. Now let us try to find the charge acquired in microcoulomb. The charge acquired in microcoulomb, okay, by the capacitor after 5 microseconds is. I think all of you understand that question clearly. Okay. So look at this, all of you. Some options are given actually here. This question was asked in, this is the 40th question and this was asked in IES, okay. And the option A was given in 7.5, B was given in 13.5 and C is given as 14.5 and D is given 15, okay. The charge in microcoulomb is asking, okay. First read the question here. The charge in microcoulomb acquired by the capacitor after 5 microseconds. Generally, when current versus time is given, charge is asked, I think by this time we are very clear that we go for area calculation. But now the area, should we calculate from 0 to 5 or 5 to 7? That is the question again. From the data given, is asking charge in microcoulomb acquired by the capacitor after 5 microseconds. Yes or no? He is mentioning that. After 5 microseconds means what? Would you like to go for 5 to 7 or 0 to 5? See, according to the dictionary meaning, after 5 microseconds means it looks like 5 to 7. Okay, but don't go by the dictionary meaning. Go by your common sense. That suppose you have your mobile. Okay, the mobile battery was completely discharged, let us say, and you want to charge it. You charge for 2 hours, let us say. You charge for 2 hours. If I ask you what is the status of the battery charging after 2 hours, what does it mean? Is it not again within these 2 hours? Sir, no, all of you. What is the battery status after 2 hours? After 2 hours means what? Within these 2 hours only. As far as battery charging is concerned, okay, when it is related to the battery charging, you must always interpret like this only. Understand? Okay. Well, so therefore, It is not 5 to 7, it is 0 to 5 only. But 0 to 5, the area, 0 to 3 we know very well. 3 to 4 it is a trapezoid, this is triangle, this is trapezoid. But 5 we need to project. If you project here, definitely this is going to be what? 4. How you know that is 4? Because it is between 3 to 5. The y-axis limits are what? 3 to 5. The x-axis, okay, limits are what? 4 to 6. Then obviously, if you extend it, it will be intersected at 4 only. Actually, this was given 2 and 1, something like that, okay. It doesn't matter, but this is very, very important here. Now, if you take the area, this is area 1, this is area 2, this is area 3. Now, Q of 5 is given as Q of 0 plus area over the limits 0 to 5. But no information regarding initial charge. You can say area 1 plus area 2 plus area 3. Yes or no? Now, what is area 1? Half into BH. This is 3 into H. How much here? Okay, 5. Plus area 2 is how much? Area trapezoid. Height is 1. 1 by 2. A is 5. B. What is that B? B is 3. Plus again one more trapezoid. Yes or no? Half. A is how much? 4 plus 3. Okay. Therefore, this is actually, 15 by 2, 7.5 plus, okay, 8 by 2. What is it? 8 by 2. What do you get here? 4 plus, what is 7 by 2? 3.5. Yes or no? 7.5 plus 3.5, 11, 11 plus 4, 15. 15 microcoulomb. Why microcoulomb? Amperes into microsecond will give you what? Microcoulomb. That's it. Note down that. Note down that. Note down that, all of you. Hope you understand why I am taking from 0 to 5. As far as battery charging is concerned, even if it is mentioned after 5 microsecond, what is the charge acquired with the capacitor? After 5 microsecond, that is nothing but between 0 to 5 only. Bulb. So I think all of you finished that. Bulbs. Okay, we'll go for the topic bulbs. Bulbs means only tungsten filament bulbs. Understand all of you? Okay, only tungsten filament bulbs we are going to discuss here. Okay, tungsten filament bulb is represented like this. Normally, when the bulb is given, he will mention clearly the voltage rating and power rating. Rated current generally won't be mentioned. But generally, voltage rating is very, very important for the bulb. Power rating is also mentioned, okay, on the bulb. Generally, these bulbs now, tungsten filament bulbs are not in use, I think. Particularly in cities, nobody uses. Everybody is enjoying what tube lights as well as, the LEDs. Okay, LEDs and tube lights people are using. But when you go to the remote place, remote villages, definitely people are using tungsten filament bulbs only. What is the reason for that? The remote villages are still, facing the problem of what? Low voltage issues. Under low voltage condition, the tube or the LED, they won't glow properly. They simply flicker. So this is very important thing. In interview, people may ask you that where people are still using the tungsten filament bulb and why they are using it. In villages, remote villages, people are still using only tungsten filament bulb. This is the only bulb which glows even under low voltage condition. Of course, the lighting effect will be little lighter, okay, because the illuminance of that particular light will be lower, no doubt, but definitely it will glow. But whereas the LED and the tube, they won't glow properly. They simply flicker. That will cause, that won't give you, or that won't solve your purpose. That is why People still use tungsten filament bulb in remote villages. Okay, but when the bulb is given, generally voltage rating and power rating are mentioned, and once you know the power and voltage, you can find okay, resistance of the bulb. Okay, this is called cold resistance again, because when the bulb is operating, that gets heated, and the resistance is a function of temperature. The resistance may also vary again. Okay, but here I'm finding using this simply rating, therefore not considering that heating effect, I may get cold resistance, and again hot resistance can be determined by multiplying the cold resistance by a certain factor. Okay, so what do you understand from this? Because voltage rating of each and every bulb is same, because all bulbs are connected in parallel in our domestic purpose or any purpose, except in special cases where the bulbs are connected in series. Okay, but most of the cases the voltage rating is same because parallel combination. Then R is inversely proportional to power. R is inversely proportional to power. Then what does it mean? The bulb with 40 watt will offer higher resistance than the bulb of 60 watt. 60 watt bulb offer lower resistance than that of a 40 watt bulb. Okay, so this is very, very important here. Now the questions are coming on the bulbs. Okay, the questions are coming on the bulbs here in this way. When the bulbs are connected in series, which one glow brighter? When the bulbs are connected in parallel, which one glow brighter? Like that, you can expect the questions in the exam. Okay. Understand? Okay. Now, series combination of bulbs. First one we'll see series combination of bulbs. Series combination of bulbs. Okay. What happens when series combination is taken here? Obviously, when the bulbs are connected in series, the current is maintained same, but the voltage gets divided. Yes or no? The voltage gets divided. Okay. This is the operating voltage. And the rated voltage of the bulb will be definitely same as the rated voltage of the second bulb, right? Both the bulbs are rated at same value, no doubt. But power ratings are different. One is 60 watt, the other is 40 watt, it might be. Yes or no? Then, what do you get here? You get R1 is nothing but VR square by PR1, and R2, you can find VR square by PR2. Yes or no? Okay, this is one thing. And I want to find the power and compare how these two bulbs are consuming. In order to compare, okay, I have a formula, P is equal to I square R formula as well as V square by R formula. So which one do I prefer to compare? Especially when you have a series combination. For series combination, the current is same, the voltage gets divided. Therefore, let me prefer this formula here. So what is actually P1? P1 means consumption, not rating. Okay, power consumption is different from power rated. Okay, when the bulb is experiencing the rated voltage, the operating voltage is same as rated voltage, then power consumption will be same as what? Okay, power consumption will be same as power rating, no doubt. But here, the bulb voltage, the operating voltage is V1, it's not VR. Voltage gets divided here. Yes or no? Therefore, power consumption can be calculated here. I square into what? R1. And power consumption of the second bulb is what? I square into R2. From this, we understand that power consumption is directly proportional to R. From these two, you understand already here, you already know that R is inversely proportional to what? PR. Yes or no? R is inversely proportional to PR. From these two formulas, you can say that power consumption is inversely proportional to power rating. Yes or no? Okay. Now, we understand which bulb is going to consume more power here. A 40 watt bulb or 60 watt bulb. The bulb which is having a lower power rating will consume higher power. Therefore, power consumption of 40 watt, okay, will be higher than power consumption of 60 watt. That means when the two bulbs are connected in series, okay, 40 watt and 60 watt, 40-watt bulb will consume more power, and the power consumed with the bulb will be dissipated in the form of both light as well as heat. Therefore, a 40-watt bulb, okay, bulb glows brighter. 40-watt bulb glows brighter. I think you understand this, okay? So this is what the concept here, the bulbs. We concluded that power consumption is inversely proportional to what? Power rating. From these two, we have derived that, and finally we conclude that when the two bulbs are connected in series, or n number of bulbs are connected in series, which one glows brighter? The bulb with a lower power rating will consume, okay, higher amount of power. Therefore, that will glow brighter than any other bulb. So this is what the conclusion. It's very, very important. All of you please note down. And I stop the session here. You please note down this. You have still time. Please note down. I stop the session. In the next session, I will see the parallel combination of the bulbs. Okay. And after that, we will see some problems. Okay. And with that, the entire fundamentals of DC circuits topic is over. Okay. Please note down quickly.